So, dear students, very good morning to all of you. Welcome to the day 14 of the digital hardware design course using VHDL for 40 hours. So, if you remember that yesterday we were discussing about the counters, okay, right? And just to give a brief review about it, counters can be used in various places in day-to-day life. Okay, they are having very real-time examples. And it is a electronic device which can be used for counting the number of clock pulses, events, or can be used for uh, generation of delay, frequency division, and generation of clock and as well as digital timers in microprocessors. So counter is having different types of application because it is a sequential device. So it can be built upon using the fundamental flip-flops, fundamental blocks, that is flip-flops. We have also covered the types of counters. There are different types of counters: asynchronous, synchronous, up, down, mode, and ring and Johnson. Yesterday we have focused on asynchronous counters, ripple counter, how it works, a 2-bit ripple counter. We have seen its VHDL coding using structural style of modeling, as well as we have also seen how verification and simulation. During the asynchronous design of the counter, we came across the concept that it can also be utilized as a divide by 2 clock divider. Okay. Similarly, we have also focused on synchronous counters. There is a difference between asynchronous and synchronous counter. That is, in asynchronous counters, the clock pulse of first flip flop is, is given by the clock, but the clock pulse of the second flip flop in asynchronous counters would be the output of first flip flop. But in asynchronous counters, all the flip-flops will get the same clock pulse. However, in it, the output, the first flip-flop output becomes the input of second flip-flop. This we were discussing. This is the example of synchronous counter, a 2-bit synchronous counter. Yesterday we were designing that, okay, and what we have seen that while designing, we came across that the logic or the functional verification is not correctly verified, okay, or not correctly done. Why? Because there is some glitch or there is some error while functional verification, right? So let's see what was that glitch and how do we can remove that. Okay. So yesterday, if you are seeing that we were focusing on designing of synchronous counter like this, and in it, what we have two flip flops because it's a 2-bit synchronous counter. In these two flip flops, one flip flop is both these flip flops are T flip flops, but they are connected in such a manner that they are acting as a 2-bit synchronous counter. The logic behind this is when you will apply the clock, initially they are having 00 value over here, as we can see on applying the clear signal. But when you will apply clock to first flip flop, it will get toggled every time because its inputs are always connected to logic 1. Okay, it is permanently connected to logic 1. So whenever you will apply the clock, its output is going to be changed. Suppose initially its output is 0, let's say, then at every clock you can see it is toggling 0, 1, 0, 1, 0, 1, and so on. Okay, we know that as per the truth table of T flip flop, okay, let me draw for you. Okay, truth table of T flip flop. This is T out input, this is Qn, let's say, and this is Qn plus 1. next state. Means if present state is 0 and your t is, let me clear this and rewrite this. We need to check what is the present input and what is the present output so as to get the next output. What would be the upcoming output? Okay, this is how the sequential devices works. So these two inputs will make four combinations: 0, 0, 0, 0, 0, 1, then 1, 0, and 1, 1. Okay, when you have a valid clock signal, when you have a valid clock signal is negative as triggered. So when you have a negative as triggered or a valid clock signal, every time, every time it works. Okay, this is the negative as triggering. You can see over here, just to show you change in transition. I'm showing you the change in transition. So this is a valid clock signal. Okay, right? Okay, and I'm assuming that in all these cases there is a valid clock signals coming over here. Okay, there is a valid clock signal coming over here. Just trying to write the truth table of T flip flop so that you will understand where we are missing the why we are not getting the correct output yesterday, so that you will understand. And for that, it's important to understand the truth table of this T flip flop. Okay, right? So you can say when valid clock signal is there, there is something should be at the output. We know the output will toggle when T is 1. Okay, so if present state is 0, it will become 1, or if it is 1, it will become 0. Similarly, when both inputs are 0, similarly when T is 0, the output remains same. There is no change in the output. It will follow the previous value. But if we will see closely, watch this, it will resemble us the truth table of XOR gate also. So we can say that over here, we can say that from here itself that the concepts of these concepts maybe have learned in your digital electronics. Just I'm revisiting them so as to get the final output. So what we are saying that actually actually it is acting like this, right? This is the truth table and it is resembling the XOR gate. Inputs are XORed with the past output. Okay, so only this concept we have to apply in our program and it would work. You can see over here what we are doing. We are assigning T, clock, clear, Q for a single flip flop. Okay, and what I am doing, I have, let me make it variable. Yesterday we have made it variable, so make it variable only. Variable u std underscore logic. Okay, initially, let's say I am assuming when clear is 1, as per this diagram, when clear is 1, outputs are reset. Both the outputs are reset. Okay, So both the outputs are resetted. So for that, for the time being, because I'm designing it for a single T flip-flop, first of all, so I'm assuming the output is reset. The output is reset. After that, whenever you will apply the clock, whenever some clock comes, it is always going to toggle. But when you will apply this type of identity only. Okay, so I need to apply if initially output is 0, which I am storing it in an intermediate variable u, for example, then this intermediate variable will update again its value depending upon what is the value at the input t XORed with previous output. Okay, right? Previous output. So that will get the next output. It is like the same thing which we are written over here, the next state and the previous state. Okay, so now next output we are going to get, these are the same thing, but presently what it is having and what is next it is going to t. So let's just they are denoting qn plus 1 and q1. That's why we have taken u variable both sides, because it is acting like an input and output. Okay, so it should follow this identity. So this is the catch that we were missing yesterday, right? After that, once our process is if is ended, we have updated this u value in the final output q. Okay, whatever the scenario is there. Okay, depending upon the whether it is clear equal to 1 or whether it is having a valid transition, whatever the value you will get, it will be updated into the final output, which is inside our end. This is the important thing that we were missing yesterday. Rest of the things, there is no change. That's it. It will work now. I have already tested, uh, but for your reference, I will again try to demonstrate you with the help of software. Okay, let's see. Let's wait for some time. It will take some time. Okay, so let me open the same project that we were working upon yesterday. Sorry. If you have remembered, yesterday I have created a project with the name S count and I have created a T flip flop in it. Okay, so in this, I have already done these changes. You can see right over here. Already I have done these changes. I just need to simulate final program and check it out whether it is perfectly working or not. Before simulation, let's check it out. Is there any change in the hardware schematic or done by the synthesizer? Because we have added a XOR gate now intermediately. So definitely there would be some addition in the hardware. So that we need to verify. Okay, so you can see and closely observe, okay, that the output of this Q is connected to this T flip-flop. But if you will go inside, you will find that okay, there is now XOR gate is connected. If you remember that during your digital electronic course, you have done conversions from one flip-flop to another flip-flop. So basically, in this VHDL or in this software, there is a D flip-flop available, and it will design all the flip-flops using this D flip-flop itself. Okay, so you can see over here when you will when you have learned the conversion of flip-flop in your course. So in that you have learned to convert a D flip-flop to T flip-flop. So it looks something like that. The XORed with the output and T, it will become a T flip-flop, right? So same thing is done over here, right? This I want to show to you. This is the change that happened in it, right? That's why our logic will now will work perfectly. Okay, let me take a snapshot of this so that you will have a reference. Okay, now let us simulate this design. Okay, for this we need to go to simulation. Now let us see. Make TA as 1, right? Make TA as 1. Okay, now make clock. Initially make it 1 also. After that we'll make it 0 for a valid transition, and also make this clear active by applying 1, so that when I will run for a short duration, the outputs are cleared. You can see over here the outputs are getting started with 0 0 0 0 0. Now after that, let's make the clock to transit from 1 to 0 over here and make disable this clear signal. Okay, now again run for a short duration. Now you can see perfectly it is working. Your output is getting 0 and 1. Okay, you are getting 0 1. Now again make transition on the clock whenever there is a valid transition comes. So for that we need to make the clock 1, run for a specified time, and again make the clock 0. Again valid transition comes. Again there is a valid transition. You can see as valid transition comes, again there is a change in the output. Now it will become 1 0. So 0 0 0 1, and now 1 0. Last what we have left, it is 1 1. Both output should be 1 1. So you can see again, make it 1, run for a specified time, and again make it 0. Okay, and run for a specified time. So now you can see both the outputs are 1 1. So if I will sweep from here to here, you can see 0, 0, 0, 1, 1, 0, and 1, 1. You can check these outputs, right? Again, let me show you again how these are changing. Okay, just closely watch these outputs over here. 0, 0 initially, 0, 1, 1, 0, and 1. Perfect. It is perfectly. You can take the snapshot of this for your convenience so that right. Okay, so it is acting like a counter 0, 0, 0, 1, 1, 0, and 1, 1, as we have seen over 0, 0, 0, 1, 1, 0, and 1, 1, 0, 1, 2, 3. It is like when you will increase more flip flops, when you will increase make it 3 flip flops, then it will become 0, 1, 2, 3, 4, 5, 6, 7, 8. 4 flip flops, then count goes to 60. 5 flip flops, then count goes to 32. Then accordingly you can make the design. In the code, you just need to increase the number of port map statements. That's it. Okay. So this we have completed with the designing of synchronous counters. Hope you have uh, understood and there should not be any doubt in it. Okay. If you have any doubt, you please let me know. Or otherwise, we will uh, move forward with the new topic, right? That is, let's move with the new topic. That is another counter, a specific counter, which is again a application of shift register also, right? That is a ring counter. Okay, a ring counter. Why we say it is a ring counter? You can see over here, if you will closely watch this, why we say this is, it is as a ring counter. This is a ring counter schematic diagram. Okay, we know it. This is the example of a 4-bit ring counter. So you can see it is making a ring over here, closed loop. You can see it is making a closed loop over here, right? It is making a closed loop over here. So if you want to design this type of counter using simple behavioral logic, you can design that also. If you want to design it with the structural modeling, you can design that also. In my course, I will be taking you to the examples of I will be taking you to designing using structural style of modeling. Reason being, you have you have learned these type of circuits in your digital electronic course, so you are familiar with these type of circuits. So I am giving you example of these type of circuits because how do we design as it is these types of circuit in VHDL, or otherwise you can have different methodology also of designing the same thing. You can go for simple behavioral style of modeling and you can design this ring counter. Okay, we'll see that also. Okay, we'll see that also and comes and tell you how it can be done. Okay, we'll take one example of simple behavioral model also so that you will understand. For the case of this, like this, uh, mod n counter, I will let you know mod n counter. Okay, when we'll design mod n counter, I will let you know for the same can how it can be designed. Okay, first of all, but we should focus on the designing of ring counter. So in it, you can see it follows this type of sequence. Ring counter follows this type of sequence. That is 1, 0, 0, 0. Then this one is shifted to this position. Then this one is shifted to this position. Then this one is shifted to this position. And again, it will come back to the same position 1 over. So for that, what you need to do? Just push the data from here. Initially let's assume this is a clear signal. Okay, this is a clear signal. So let this clear signal to be activated and make the output of this first flip flop, because initially let us assume that its output is 0 0 0 0. Let's say initially all the outputs are 0 0 0. Okay, but suppose when we have applied this preset signal, only it is applied to first flip flop. You can see over it. Preset matlab means preset means we are going to set the output of this flip flop to 1. This sequence. So that start with this sequence. Whenever valid clock signal comes. So whenever valid clock signal comes, what we want that the output of this Q3, whenever the valid, as you will do the preset, okay, initially, so that it will is having a sequence 1 0 0 0. Now after that, after that, when you will apply a valid clock signal, this one is shifted to this point, this one, and this, the previous value of this output is shifted to this, the previous value of this output to this, and the previous value of this is shifted to this. What was the previous value? So after first clock cycle, what you will get? This one is shifted to this position, and the zero is comes to this. This zero comes to this position. So it is basically a shifting operation. It is a application of your shift register. That's it. Nothing more than that. Okay. And what we need? We need a D flip flop in it. We need to design it with a D flip flop. Okay. Right. So can we start it with this? Can we do it with this? It is very simple. If you will go or design it with the behavioral style of modeling, let me show you the example. है ना? Ring counter using behavioral style of modeling. Ring counter using behavioral style of modeling. How can we design ring counter using behavioral style of modeling? Okay, so let us start writing the code. Library IEEE use IEEE dot std underscore logic underscore 1164 dot all entity ring ring count, just I will write entity ring count is. Okay, port 4-bit ring counter. If I want to design, what should I write? Port port. We need 4-bit input. Sorry, as per this we need only 1-bit input, one input, rest of our intermediate outputs, right? Rest of our intermediate signals. So we need one input and one output, just like serial in, serial out. Okay, so we need one input. Let's say one input is, let's say, starting with uh, the initial input. Let's start with D naught, as we can see in this diagram. Okay, I will follow this. D naught and last output is Q3. I will follow this only. Okay, let's say it is of single bit in std underscore logic. Okay, right. Then what we need? I need clock also. clock, and one is preset. One is preset. 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 Not reset. It is preset. Preset. It is also input std underscore logic. Okay. Then I need Q3 simple as output out std underscore. Okay. Simple. Simple. Just I have written the entity and ring underscore count. Now let us write the architecture. Architecture of ring underscore arc of ring underscore count. Okay, because the name of the entity is ring underscore count. Begin. I should write begin. Then process. Process. In process, I need to put what? I need to put T naught. Then clock. Then preset. If I need some variable, I can do so, right? If I need some intermediate variable, and that we need because there are some intermediate output that should be reflected. There are some intermediate outputs. So I can either create a variable or I can go for design. I can go for signal. I can use any of the thing. Okay. Whether I can whether I can go for the signal or whether I can go for the uh, variable. Okay. Right. So let's see. First of all, let if I want to design it with the signal design. Okay. Signal 4 bit u colon signal 4 u colon std underscore logic underscore vector 3 down to 0. Okay, 3 down to 0. Or I should write 0 to 3 so that it will become simple for you. 0 to 3. Then process begin. I should start with the process begin. Okay, so this is the code for this now presently. Let me copy this. Okay, now after that, what should I have to write? I have to write if preset equal to if preset is active low. Active low means it is activated at 0. So I will make like this. If preset is active low means it is activated, then I need the intermediate output. I need this output. Okay. I need what? I need this type of output. It should start or reset to this position. Okay, it should start with this sequence. So I would write u colon equals to 1 0 0 0. Okay, u colon equals to 1 0 0 0. Right? U colon equals to 1 0 0 0 0. Okay, like this. And before that, what I would do, I would pass, I would start with that u of naught, which is this one, which is this one, u of naught. This is u of naught. Okay, this is u of naught, this is u of 1, this is u of 2, this is u of 3. Okay, right? So initially when it start, so u of naught, let me write the signal assignment statement. U of naught u of naught gets the value of d naught. Okay, what are the value initially at d naught? It will receive by this. Okay, let's see whether it is required or not. We'll see later on. But first of all, design this. If preset equal to 0 when it is activated, right? If preset equal to 0 when it is activated, then you update with this value 1000. It should start the sequence from here. Else if clock is activated at what point? Clock is activated at logic 0 also. So it is also negative as triggered. So clock equal to 0 and clock tick event. Right? This we have to write. Then what I want, whenever clock comes, this U value should be shifted. This U value should be shifted by one position to the right. So we can say that U gets the value of, just see over here, what should I write? Today I'm uh, telling an important operator, a shift operator. We have seen some of the previous shift operators in shift operation, like SRL, SLL. Okay, but that shift operator sometimes are not synthesizable. When you will write the code in the software, they may give you some error of library. Okay, so in some latest versions where a new library of VHDL of after 2000 is updated, there where they work, otherwise they generally not work. Okay, there are some new shift operators launched as compared to the previous one. Okay, so irrespective of that, what we can do, we can go using a simple uh, different different possibility, that if we want to shift this from this position and I want this to be this position, so what I need to do? So for that, what should I do? You can see over here, what should I write? That this value should be shifted to this position. That u of naught, I don't think it is required, like, but still, let's see. That u of naught, rather than I should, okay, I should write over here, not u naught. I should write over here. Uh, Q3 is D naught is input and Q3 is output. Uh, D naught is input and Q3 is output. Okay, we'll see. Let's design this first. So what I want, that this value, this, which is Q3, okay, which is a Q3. But over here, what it is U naught, it is U1, it is U2, and it is U3, right? So what I want, that U naught now should be updated with the value of U of 3. So U naught should be updated with the value of U of 3, and after that, what should I write? Or in other words, what should I write? U023. In this way, we can also write over here U023 should be updated with the value U of 3 at U0 position, and see what I am writing, and over here, and rest of the part will get what value? U Rest of the part will get the value of U02, means U123 will get the value U022. Am I right? Okay. So this operator, basically, this operator over here, it is called as concatenation operator. This operator is called as concatenation operator. It will basically connect two strings together. Okay. It will going to connect two strings together. Okay. Tukur, can you please unmute Mr. Pankaj Prajapati? Okay. So it is called a concatenation operator. So what it is doing basically, it is connecting two set of strings, you can say, where U3, which is over here, it is going to this position at U0. So this is U0. Okay. And rest of the values, yani means 1 to 2. This will get the value means U0 to 2. U0 to 2 means whatever the value that is previously present over here, it will be transferred to rest of the bits, means it is shifted by 1. Okay. So in this way you can write. So whenever this happen, you want to do this operation on every clock pulse. Okay. Whenever this happen, whenever clock comes, this operation keeps on repeating. Okay. And it keeps on repeating whenever the clock comes. Simple. Very simple one. Else null. Else null. Okay. Else null and if. Finally Q3, let us update these inputs. Finally Q3, initially what we can do over here, because we have used D naught over here, so let's make D naught equal to 1. Okay, let's make D naught equal to 1, because this is our input. Let's make D naught equal to 1 for from our side. Okay. Now, but when preset is there, it will does this. Okay. After that, at the end, what I need to do, what I need to do after and if, I should have to update Q3. No, I should have to update Q3. Q3 with the value of Q3 with the value of which one? U of 3. Finally, because we are getting the output from here itself. Okay. Okay. Finally, because we are getting the value from here itself. Because Q3 will get the value of U of 3. This is the final output. Okay. Because when we will get the output from here itself. And we have assumed these intermediate outputs to be U0, U1, U2, and U3. Okay. So finally, I am updating this with Q3 will get the value of U3. Okay. Right. Let's close it now. And process and architecture. And architecture means ring underscore arc. Let me copy this. Okay. So this is a simple program of ring counter using behavioral style of modeling. And I have told you a new operator today. This operator is known as concatenation operator. Concatenation operator. It will concatenate two strings. So what you can do now from onwards, if you want to do some shift operation, you can use this type of concatenation operator. It will help you in designing the shift operations in your program. Okay, this is the fundamental approach. Rather than using some macros or some functions or some operators, you can go use this type of logic also for shifting purpose. Okay, now let us test this program whether it is working as per our uh, requirement or not, and we'll see. Okay, let's see. Let's rewrite this program, create a new project. Next, let's write it as ring underscore count. Okay, ring underscore count. Yeah, ring count is the name of the project. Hardly matters, whatever you write. Over here, let's create file of VHDL. The name of this file should be match with your entity name. It is mandatory. Ring underscore count. Next, next. Select the board. Next, finish. Yes, we want to create a new project and we want to close the previous project with whatever it was there. Just pass this. We will write our own code, copy paste our own code. Let's copy paste our own code from here. Okay, you can see if it is giving some error over here. Architecture, offering underscore architecture, architecture, okay. Architecture, ring underscore architecture of underscore count is, this is the correct definition. D naught is the input. So we have applied D naught, why it is giving, okay. It should be gets a value of, okay, right. So these are the some of the uh, syntax errors, right? Okay, D not because of mode in. Okay, okay, okay. It should not be as an output. Okay, it should not be, cannot be used as an output. Okay, okay, because it is an input to our logic. Okay, so what we can say, we can write. Okay, over here, we can write. Uh, we can write over here as if we want to use this D naught as an input. So what we can do, we can pass U naught. in it u naught, the first u naught gets the value of t naught. Okay, we can do like that also. U naught gets the value of t naught. Okay, we can push the data from here also. U naught gets the value of t. Finally, we are pushing the data. U3 gets the value of U3. Okay, in it. Rest we are shifting the data simple. Okay, let's check it out whether it is working or not perfectly. First of all, check it out whether it is creating the same type of logic what we are trying to say to you. Okay, because somehow it is going to create a loop. Okay, that is there. But because Q3 and D naught are not directly connected, but they are connected with this U naught and U3. Okay, right? So let's see whether it is working or not and check if there would any error. Okay, so there is no syntax error. We need not to. We need just to simulate this. Okay, just Control S, save this project. It is asking us and start the simulation. Okay, right. So what we'll do, first of all, just pass this force constant, pass this value, we'll pass some value d naught over here to 1. Okay, we'll pass value 1 so that it should start with this. Then make clock 1, then make preset also activated. So it is activated at logic 0 because it is of active low nature. Okay, simple. Now we'll try to run and see whether it is happening or working as per our uh, need or not. So it is showing you intermediate signal. You can see over here also, and this is the final output you will be getting. Okay, so let's run for a specified period of time and see whether our output is updating as per our requirement or not. Otherwise, we need to change it. Okay, so finally Q is not updating. You can see, but our U is updated to 8. Okay, so Q3 is not updating. There is no issue. Okay, Q3 is not updating. It will be updated at the end of the program maybe, but we are getting output at this. When preset is 0, we are getting output as 1000. 100 means you can see we should change the radix of this as binary. So we are getting 1000. Okay, okay. Initially, when preset is 0. Now let's make this preset. Let's make this clock to transit, and let's make this preset to 1. Disable it because it is of active low nature. So we'll disabling it by providing 1 over it. Okay, and let's again run and see whether what we have done it is. So now you can see whenever the clock comes, it is shifting. It is shifted by 1. Okay, and your Q3 is now finally getting the output 0 because we'll get the shifted data. We'll get the shifted data. Okay, now again run this. Again apply a clock to valid clock. First one, run for a specified period of time. There is no change. Okay, now, okay. Now you can see what is happening over here. It is updating at positive edge of the clock also. Let's see, let's see why it is happening. There should not be any change over here. It should remain same. But there is a change. There is a change is there. Okay, okay, right. Why it is happening? We need to change the logic. There is some error in the logic. We can see the U is updating at every clock cycle. It is updating over here also. When preset is 0, that is fine. It should update this value. When it is there, it is there. But it should not be updated at this point. है ना? It should remain same. Why it is happening? Because of this d not equal to 1. Because it is always 1. So it is pushing the value in u naught. So we need to remove this actually. We need to remove this in the code. So let's go back, discard this. We don't want this to be there. So we do not want this to be applied over here. This is not required actually. Okay, this is not required. This is not required. If preset equal to 0, we are updating it with this value 100. It is a constant value. Okay, or we can write it as we can we need to involve this d naught somewhere somehow because it is acting like an input, but at the same instant of time it is acting like an output also. So what it should be the solution to it? Let's see. Just wait for a while. We need to actually see whether this d naught uh, because it is not an independent input and this is output. This is output always, that is true. But this is acting like an input and as well as it is acting like an output for Q3. So for that maybe we need to make it uh, maybe we need to make it maybe we need not this. We can remove this from the board. Okay, there is no requirement of this. What I would see from here, There is no requirement of this. Only this would work. Okay, this is more than enough. We need not this over here. There is no requirement of D0 because it is not explicitly available. You can see over here, it is not explicitly available as a part of the entity. Rather, it is acting like an intermediate output. It is also like an intermediate output. Okay, so we can check the output at this side, but there is no requirement of this. Okay, so we can remove it from the entity. There is no requirement of this, right? But I feel so. I don't think there is any requirement of this input in this program. Okay, anything else which I need to? This U3 is not updating still because you can put this Q3 over here also. Okay. Now let's check the program now. Again, we have done some small changes in this program, and let's see whether it is working as per our need or not. Again, we'll do the simulation. Okay, let's see. Okay. Make the radix of this as binary. Okay. Now let's start again. We should start with now clock and preset. Clock and preset. The clock, uh, initially apply this clock as 1 because it is active low. We need to create a proper triggering and make it 0. Make it activated because of it is of active low nature, and try to run for a specified period of time. Now you can see over here the output is changes to 100. Till now it is okay, right? Initially preset is 0. Initially it start with this position. Finally Q3 is not updated yet. Okay, Q3 is not updated yet. Why? Because we have not specified Q3 in preset condition. So if we want the data to be available over here also, we need to apply Q3 in preset condition also. Then it will work. Okay, we'll see that's also, or let us change it first of all. Okay, let's make change again. Small. Let's apply Q3 over here also. That's why it is not giving you correct output. Okay, now it will give you correct output. Let's check once again. change its radix to binary, apply clock as 1 initially, apply preset as 0. Okay, now try to run. Still it is not updating. There is some error. We'll see that later on whether it is working perfectly or not. Okay, after that, let's see when we are applying. Let's reset this reset, make it 1, deactivate it, and now try to apply the clock, make a negative edge transition on the clock. Okay, okay. Now you can see on the negative edge of the transition, it is working perfectly. It is shifted to 0 1 on the first clock cycle. The data goes to 0 1 0 0. Now again, now and you can see Q3 will also update it with the value 0. Okay, now what we'll do, we will put force constant on the clock, make it 1, and again make it 0. Okay, we'll again make it 0. Again run. Sorry. Sorry. We need to force constant 1 on clock and run for a specified period of time. So see, there is no change now. It is working accurately. Okay, it is working accurately. Right? Now again I will force. I will again I will make a positive transition, negative transition on it, then a valid transition, and run for a specified period of time. Now you can see the data is changes. Again it is shifted to this position. Okay, you can see now it is acting or working perfectly. Okay, the only thing that is there, that is a glitch of initial this Q3 is in the glitch. Let's see why it is happening and try to remove this only, so that it should also get the initial value. Okay, okay. So see why it is happening. Let's see. uh, Instead of this putting Q3 over here and over here, what we can do, we can put it at the end of the process, after end of the process. Maybe Q3 gets the value of U of 3. Okay, let's see whether it would work or not for us. Okay, let's see that. Again run simulation. We'll try to run simulation, check whether now Q3 is updating with the output or not. Okay, first of all, change the radix to binary. Make clock 1, make preset activated, Now run for a specified period of time. Now you can see the problem is solved. Initially, your output is also get 0. The value of U3 is updated to the Q3. So generally in signals, what is there? What is the problem? In signals, you can see that the value is updated at the end of the process. So whenever we define signal in the code, just because we have defined U as the signal in the code instead of variable, the variable will update its value instantly. Means whenever you will write this statement, it is updated at the same instant in U. But in signals, when you use signals, the value of this U not to 3, all these values will be updated at the end of the process. So that's why I have written at the after the end of the process this Q3 final output. Okay. So whenever you do shifting operation, you need to use uh, you need not to you have to use the signals rather than variables, and accordingly you have to manage your program. Okay. Now you will see when I will now make this preset disable. Okay. Let me make this preset disable and now apply this clock as a clock, force clock. Okay, force clock. Let's leading edge value is after that. Let's leading edge value is, because last time I have applied it as 1, so let's leading edge value is 0 and trailing edge value is 1. Last one is 1 and I am going to have lead edge 0, and let's apply. Okay, and now I will run this. You can see automatically this counter keeps on running. Okay, you will get this counter keeps on running on every transition of the clock. This keeps on repeating perfectly. You can see over here, whenever a value transition comes, it keeps on repeating in every cycle. 100 0 1 0 0 0 0 0 1 0 0 0 1 1 0 0 whenever till you are getting the clock, it is keeps on updating. Okay, and over here you can see also your Q3 output is updated. Okay, Q3 is also updated with after four clock cycles. Means you will get that value 1 after 4 clock cycles, and where you are getting over here after 4 clock cycles you will get the output 1 in Q3. In the fourth clock cycle you will get the output. So each after every 3 cycles you will get the output in the Q3. Okay, I hope you will get this point what I'm trying to say to you. Okay, is there any doubt in it? Please let me know if you have any doubt. I think it should be clear to everybody. So see, I have made the changes in the program because my functionality is not being verified properly. So we cannot escape until and unless we are fully satisfied that whether our design is perfectly working from all aspects. We cannot skip. Okay, we cannot go up because it's okay. It will, it will, it will. You can go to the next step because there is not any syntax error or there is not any other thing. But the logic is incorrect, and if the logic is incorrect, means whatever the steps that you will follow further, these all becomes incorrect. There is no use of these all steps further. Okay, whatever the design that you will create, schematic, that is also incorrect because somehow your logic is not working, and your logic depends upon the hardware circuitry that you have generated. So if your logic is not working, it will also if your logic is not correct, and if you have generated the hardware and download that program into the FPGA, so the FPGA at the hardware also you are not getting the correct output for some of the inputs. Okay, so this must be checked and verified fully in all aspects before jumping directly onto the next level. Okay, hope you got my point. What I'm trying to say to you, these are some of the important observations and aspects of designing the things in VHDL, and I'm not using some ready-made programs. Okay, I'm writing the programs on the live for you people. Okay, so that generally what the types of mistakes that I encounter now itself after being so much long experience also, still I encounter with these type of mistakes, because when you will in touch, then only you will get the being things being fed into your mind. Okay, keep on practicing. When you will keep on practicing, then only you will find, okay, this type of logic should be applied that side, this side. But your fundamentals should be clear about the language and about the digital hardware or digital circuits. Okay, I hope it is clear to everybody. If you have any doubt, please let me know. Any doubt, please confirm. Please write in chat box. So you can see we have designed this time this string counter without using the structural style of model. We have designed it simply with the behavioral style of model, where I want to give you the example. Okay, we can design this type of circuits using behavioral style of model also. Okay, not a structural style of model. We have designed it with the help of behavioral style of model. But you can design the same circuit with the help of a structural style of model also, right? Yes or no? You can try by yourself that approach and check whether your design is. So what we have learned in this, we have learned a new operator, concatenation operator, where you will concatenate two strings. It is simply an AND operator, but when you will use this in this manner, this operator in this manner, it is actually used as a concatenate operator. Okay, if you want to check this schematic in this design, you can check this schematic also. See, this type of design is there. Okay, it occurs with this type of design. You can see it is showing you that there are four such flip-flops. Okay, because we have not created with the help of a structural style of modeling, so it is showing you the same structure with some different approach. Your output is going to the input D3 first one only. Clear a clock, negative estimate. Preset also negative. It is also going on into the first, but rest of them are, you can see there is a four such flip-flops which are available, but these are not shown side by side. Rather, they are shown stacked in a stacked manner. Okay, so it is the same architecture, similar architecture, but shown in different manner. That's why I used to prefer to tell you in structural style of modeling, because the design that you are seeing and design you are getting both are same in that particular case. Okay, is it clear? Can we move forward with the new topic? Please confirm yes or no, or is there any doubt you want to ask something? Sorry, if you have any doubt, please let me know. So this is the functional verification of functional verification of ring count. Functional verification of ring count. Okay, I hope it is clear to everybody, right? So I'm moving forward. Okay, the designing with the Johnson counter. Now you can see this is the example of Johnson counter. It is very much similar to the ring counter. You can see there is a ring counter. Its Q3 output is going to D naught. But in that particular case, in the case of Johnson counter, we have the same flip-flops. The only difference is that the Q bar output is going to D1. That's it. Okay, that's it. Means you have to made a very small change in it. Very small change. Okay, in the program in order to generate this type of output. What you want initially your output should be resetted with the 000. Okay, initially your output should be resetted with the value 0000. Okay, your output should be resetted with 000, right? And okay, and after that it will follow this sequence, and it keeps on repeating this sequence again and again and again and again and again and again and again for you. So rather than resetting it at this side, what we have done at the last flip flop Q bar output, we are taking as an input. Okay, last flip flop Q bar output we are taking as an input, and we are getting rest of the output from here itself. This is Q1, Q2, Q3, and Q4. So you can design the same Johnson counter using the same approach. Okay, you can design Johnson counter using the same approach. Can you do that by yourself or try yourself? Tell me, students, do you want to try by yourself? Okay, so you will try to write by yourself. I will just give you a brief logic. How can you do that? Okay, over here, what changes you need to make in this program? I will give you, but you simulate it by yourself. Okay, you try to simulate by yourself. I am just giving you the logic so that you can try by yourself. Okay, the same program is there, the same structure is there, some same is there, but only the sequences need to be changed. So let's write this Johnson count. So just to make, we are making a Johnson counter. Okay, try to use this logic, or you can generate your own logic also, right? And give me the example whether it is working or not. Instead of preset, now we can, what we can do, we can write reset, because there is no preset, but we can introduce one reset in this design. We can put a reset in the design over here. Okay, let me insert for you so that you can remember this. We can insert a retest reset. Okay, sorry. Okay, we can insert one reset in it. Instead of preset, what we are doing, we are putting one reset in it in the design. Okay, let's say this is reset. Okay, let's say there is a one reset. which is applied to all the inputs. You can make it as either as an active high or you can make it either as an active low, whatever you want. Okay, so reset, okay, clock. So I would write reset equal to 1. Let's make it active high. Over here, I would write now when reset is 1, I want the output, intermediate output to be 0, 0, 0 as per this sequence. It should be initialized with this. But after that, whenever clock pulse comes, what I want, whenever clock comes, it should start with this position 1, 0, 0, 0, 1, 1, 0. Means I want this to be shifted at every time. Okay, I want this to be shifted at every time. So what should I write? What should I have to write? U not to U3. Okay, I want this to be shifted at this, the last flip flop output. I want this to be shifted at this in previous case. But I don't want this. I want this. So this is nothing but this is the complement of this output. You know, this is the complement of this output. So what I would write, simple what I would write, not of U3. I want this not of U3 every time. Not is a, there is a not gate, a keyword. Not of U3 should come. The complement of this should come at this position, that U naught, and rest of the bits are similar. And whenever you, till this clock is applied, let's say make it positive as triggered, because in the diagram it is a positive as triggered clock. It will keep on doing this part every time for you. And finally you will get the Q3 output from here from U3. Okay, and intermediately you can see the output from this side. So you will try to run this program by yourself. I'm just okay. I'm just giving you for your self verification so that you can check it out whether it is perfectly working or not. You just, this is a small thing, that the small change that you need to create. Just remember this in the previous program, in the logic, main logic. है ना? In the main logic, you need to do this, right? And these changes I have made in the previous program. Rest of the things are same. You can see. And definitely it would work. I am assuring you, it would perfectly work as we did in the case of ring count. Okay, this logic would work in the case of ring count. The only responsibility of yours is to simulate this and test it in the software by yourself. This is giving, I'm giving you self assignment for this. Okay, we'll try to do it by yourself. Okay, just change this ring to Johnson. Okay, I have made the changes at the required places. You can see. Okay, this will become a Johnson. Right? So I hope everybody is clear about it. Is there any doubt in it? Please let me know. Sure, Umang. Please try yourself. And I hope you all will do it. Okay. I'm assuming that all are listening carefully this course and all will be at the end of this course are expert in VHDL, right? In the digital electronics and as well as in the as well as in the VHDL at least. Just only you what you need. Only you need practice. The basic concepts and the practice. Am I right? Now we are left with only one counter. Let's do it that also. Mode and counter. Mode and counter. Have you heard this mode and counter previously? Anybody? What is this mode and counter? What does it mean? Mode and counter. Mode and counter. Mode and means mode and counter means you can restrict the count. you can restrict the count. Suppose you are designing you are using three flip-flops. So you know these three flip-flops can create a count of, this is just like your synchronous and asynchronous counter you have designed. Okay. So in that, what you have seen that if we are using two flip-flops, we can go maximum up to four count, 0, 1, 2, 3. Now, if you will using three flip-flops, then you can go maximum up to eight count. Similarly, four flip-flops maximum go to 16 count. Okay, but if you want to truncate this count, if you are using three flip-flop, but if you want to truncate this count at five or six, okay, so that would be termed as mode six count or mode five count. Suppose if I am saying you are designing a mode 10 counter, mode 10, suppose you are designing a mode 10 counter, mode 10 counter, mode 10, suppose the value of n is 10. That means, that means your count goes up to, goes up to from 0 to, from 0 to 9. There would be total 10 counts, not 0 to 10. This you have to check it out. Goes up to 0 to 9. And again, it will come back from 9 to 0. So it will count like this. It will count like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And after that, it will come back to same position over here. That is 0. Okay, it will come back to the same position. It will start with same position, that is 0. That is what we mean by mode counter. You can restrict the states. This mode 10 counter requires how much flip-flops? This mode counter requires four flip-flops, right? It requires four flip-flops at least. Okay, because after 8, it requires one more flip-flop to store 1009. Till 8, it can store, sorry, till 7, it can store, okay, three flip-flops is okay. But when 8 and 9 comes, it will require one more flip-flop to store the count 100 and 1001. Okay, so it may require four flip-flops. Maximum count using four flip-flops can go up to, maximum count using four flip-flops can go up to 16. That is 0 to 15. Okay, that is 0 to 15. What should I write? 0 to 15, right? Like this. Total 16 count would be there. But we need to restrict the count till 9 only. Count till 9 only. Okay. So this type of logic we have to apply. Yeah, required four flip-flops. It requires four flip-flops, and maximum count that you can go with this is, but we need to restrict the count till where? Till 9 only. Similarly, if you are going to design mode 5 counter or mode 10 counter, accordingly 1 minus n minus 1, you can go up to 0 to n minus 1 count. Okay, you can go on to 0 to n minus 1 count. Okay, so count should be, let me write over here, count should be 0 to n minus 1. 0 to n minus, right? I hope it is clear. Okay, right? So they can be of two types further, right? They can be of two types. If they are up count, there may be up count and down count, whatever you want to do. Or you can create up and down count both also. Means they can count from 0 to 9. So this is called up counter. Or they can count from 9 to 0. They can count from 9 to 0 also. है ना? That means down count. So you can create any type of count, up count or down count, using this mode counters as well. Okay, so let us take an example of mode 10 counter and how can we design that? Mode 10 counter. इसको decade counter भी बोलते हैं. It is also sometimes termed as decade counter. It is also sometimes termed as decade counter. Okay, so we need to write the code for this. Decade mode 10 up counter you can design or down counter you can design. First of all, we are designing the up counter. Okay, let's see how can we design a up count. Mode 10 up count. Okay, so how can we start the approach? We can go for either behavioral style of modeling. We can go either for structural style of modeling. But structural style of modeling generally we go when we know the internal architecture. But suppose if we doesn't know the internal architecture or we doesn't remember the internal architecture, because as we keep on increasing the complexity of the designs, sometimes it is difficult for remembering these the internal architectures of all the circuits. So in that particular case, what we'll use generally we'll go for the behavioral approach. है ना? So for that what I would what should, for that what I should write or what should I should go for. Let's start writing the code over here using the simple approach, just we did in the case of over here. So let me copy this. So let's say I want to design a mode counter, mode 10 counter. So I would write mode 10, simple. Clock reset, I want only clock reset in this counter. And output, I want this to, let's say I will be making this output. I will be using this as an 4-bit output. Okay, because I'm going to design the counter just like in this manner. I don't know the internal architecture. I'm designing it simple. This is my counter. Okay, this is my counter, mode 10 counter. Suppose, and in it, I am having inputs, two inputs only. One is clock. Okay, one is clock, and another is, let's say, reset. One is clock, and another is, let's say, reset. Simple. Okay, one is clock, and another is reset. and I want this to be as an output. Okay, let's say this is my input and this is my output. This output I am assuming that is a 4-bit because I need 4-bit count. Rest I have a clock signal and a reset signal. Okay, I have a clock signal which is a positive S triggered clock, and I am having a reset signal. Okay, simple. This is a I am going to design now with the help of behavioral style of model. Okay, right, and this is a 4-bit. Let's say its output name is, let's say, 1. We have two inputs, clock reset and one output of 4-bit. So let us design this. How can we design the same approach over here? Mode 10, let's say design mode 10. My output is, let's say, y out std underscore logic, std underscore logic 0 to 3. Okay, similarly architecture of mode 10 underscore arc of mode 10 is, in this also I am going to use u std underscore logic underscore vector of 0 to 3, then process clock or reset begin. I am saying if reset equal to 1, okay, if reset equal to 1, what I am doing, I am making this u signal to be 0 0 0. Else if clock equal to 1 and clock tick event, then what I am doing, I want to update this count. I want to update this count by 1. I want this count to be updated by 1. Okay, so I want this u gets the value of u plus 1, 0 0 0 1. Every time it updates it count. Okay, so it start with 0 0 0 and it's keep on repeating 0 1 2 3 4 5 6 7 and so on so like. But if I will not restrict it up to 9, then it keeps on counting. It keeps on counting. It will not stop. So for that, what I need to do, in it, I need to restrict it this count. What I need to write, I need to write if this u is equal to, if this u is equal to 9, है ना? If this u becomes equal to 9, है ना? Then you keeps on doing, then if u is, sorry, if u is not equal to 9, then what you can do, you keeps on doing this thing. Else, I'm writing else for this if. Else, when it will become 9, what I want, this u to be again reset to the 0 0, right? And if I'm ending this if, rest of the things are same. Finally, I'm updating this y output with the value of this y output with the value of u full. Okay, this y with the value of full, right? Okay, the simple program to understand. You can change the condition also. You can write over here if u equal to 9 over here, and you can change these condition from here to here also. That is also true. If u equal to 9, then u gets the value of 0, 0, 0. Else, you can put this condition over. So you can change it vice versa. So this is a very simple logic of a mode 10 or decade counter. We can test that over here. You can, if you want, we can test that in the program in our software. Okay. So for that, let me close this and let me create a new project. Okay, let me create a new project. File, project, new. Next. It is mode 10 count. Hope you will try to mode 10 count. You can try rest of the modes by yourself. Even you can design any sequence counter you want, whatever the logic you want, you can give any sequence counter is also there. Okay. For the timing, I am using the same entity name. Okay. VHDL. Next. Next. Check the board. This process we have to do. We have to repeat this process whenever you want to create a new project. Okay. Yes. So it will close the previous project and we'll write our own entity and own code. We'll copy paste it. Now see. Control A, delete. I'm copying this. If there are any syntax error, it will show us in the software itself. There is a syntax error. Its name is mode 10. Okay. Why output is not declared? But we have declared it over here. Architecture of mode 10. Architecture mode 10 underscore arc of mode 10 is. Let me correct that also. And why it is saying std underscore logic is not declared. Okay, we need to write vector over. Sorry, vector. Please correct it. We need to write vector over here. It should be vector. See, if it does any mistake, it will give us an error. Okay, syntax error. So that's why it is very important to test the things over here itself. Now what is it is saying? Found zero definition of operator. This operator cannot be defined. Oh, it is saying it is not defined over here. Okay, and it is also not defined plus operator. Why it is saying? Because we have not included the necessary library. We need to include the necessary library over use IEEE dot std underscore logic. Okay, so it is showing lots of library. You can write unsigned dot all. So these all are available inside this unsigned library. You can see now error removes. Okay, so uh, we need to include that library also specifically for some of the operators, right? Okay, so now it is my code is ready. Let me check it out whether it is perfectly working or not. For that, run simulation first of all. Okay, so we need to first of all make clock 0 because it is a now positive as triggered clock. We'll start with 0. Then we'll start with reset equal to 1. Okay, 1. Let's make the syntax of these radix of these as a as a, as a, as a as a decimal so that you can see whether it is acting like a counter exactly as a counter or not. Okay, unsigned decimal I have done. Okay, now run it for a specified period of time. So you can see it is starting with the value 0. Perfectly, it is starting with the value 0. After that, on reset, it start with the value 0. Okay, now after that, what we will do, we'll make this reset to permanently 0. Okay, and apply this clock over here. And I am applying it as a force clock, where the leading edge value should be, previously I have applied 0. So the leading edge value should be 1. The trailing edge value should be 0. And it just start from here. Now I am applying for a specified period of time. Now you can check it out. It is perfectly working as a counter. You can see. Are you getting my point? You can see over here on every positive edge of the clock, the counter is updated. This is intermediate variable and this is the final output. You can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and again 0, 1, 2, 3, 4, 5, 6. It is not like that, it is repeating with some other value. Okay. So this is the example of what? This is the example of mode 10 counter. Specifically, if I would say mode 10 up counter. It is a mode 10 up counter. Okay. It is a mode 10 up counter. If you want, you can design or try it with different modes. Even you can try it with the different sort of uh, you can try it with the down count also. Okay, you can try it with the down count also. So for down count, if you want to make what changes you will create, this is a up counter, decade up counter. What I would if I would like to make a down count, so for that, instead of starting it with the value 00, you can start with the value 1001. And whenever the clock tick event, then if u is not equal to 0, then what you can write, u minus 0000. So it will down count. Else, again, you can put 10001. I hope you can do this in this manner. You can test it by yourself, everybody. So that will become a down count. Okay, that will become a down count. Can we check the schematic also for this in 1 minute? And till that, if you feel have any doubt, anybody, please let me know so that we can entertain your queries and I will try to give the answer. If you have any difficulty, if you're feeling anything, so this is the internal architecture. See, when you are doing with the behavioral style of modeling coding, you're getting these type of internal architectures. It will design or use internal resources, whatever it is having in it, okay, in order to upgrade this type of code, okay, in order to design this. So if you want, you can create or keep this also for your reference, okay, right? Okay. Functional verification of If you have any doubt, please let me know fast. Sorry. Or otherwise, we will be closing this session soon. If you have any doubt, now I will entertain the query with you. So today, if you will see, we have designed ring counter, we have designed Johnson counter, we have also designed mode counter. Okay, you can try by yourself the mode 10 down counter also. So we have completed all types of counters now till date, the counters that we have available. In the next few lectures, we will be discussing or going to discuss about the, now you can see our flip-flops we have designed, registers we have designed, counters we have designed. The next thing that we have left is the designing of memories or register array. How can we design memory and register array? Okay, fine. So thank you so much, everybody. I'm closing this session for the day. If you have any doubt, you may raise your queries. Dr. Tukul, please close the session if there is no doubt.